So thanks everyone for being here, and I'm pleased to be here at the symposium to talk about what we have been doing on blue waters for some time. First, of course, I'd like to acknowledge NSF for support through the PREP program as well as the Fluid Dynamics program. And I've brought so many people on the Blue Waters team, and as well as Quay, they have been helping us with how to run the code faster, how do we get access to a particular part of the machine, how to and respond to my requests very quickly all the time, and as well as be very flexible about storage and helping us with doing the visualization. Of course, the other people on the slide, on my top slide here, also made contributions. Some of my, in particular, my collaborators and also my graduate students. Some of those work at a different time zone last night to try to help me finalize a couple of pieces of this. When I started the program, I was so pleased that I'm the second speaker talking about turbulence. So you all have heard about some turbulence already. And I'm going to emphasize the Reynolds number, but let's say if we want to use the one word to describe what turbulence is about, it's essentially disorder, it's unsteady, three-dimensional, multi-scale, or a continuum range of scales, and highly nonlinear. And that is prevalent in many fields of science and engineering. Here I pull up some images from the Wikipedia page on turbulence. On the left, the first one, I think we are seeing mixing in the jet, which is fundamental to the operation of a jet engine. In the middle, there's a submarine. I think the Navy wants to have less of that turbulence because they want to be not quite noticed. On the right-hand side there's an aircraft taking off, and there's a vortex. And this vortex is one of the reasons for flight delays, because you must, on the same runway, you must have a minimum time separation between one airplane and the next one. And high Reynolds number, well, what is the Reynolds number? Here, the velocity times the length divided by the viscosity. But most flows that are realistic, usually the Reynolds number is very high, thousands, tens of thousands or more. And you have a wide range of scales. So basically, you think about a sine wave or a Fourier decomposition of some kind. You have low wave numbers, you have high wave numbers, or you have low frequencies and high frequencies. And the higher the Reynolds number, the more uncertain it is, and the more uncomfortable we feel when we are sitting in an airplane. And that also implies a larger number of degrees of freedom, and all these things, as you can see, would add up to the problem of something that demands a lot of computational power. And I would like to focus for at least half of my talk on the idea of what we call extreme events. I know we talk about extreme scale computing. What is extreme? Extreme is something of a high intensity where if everybody were doing petaflops, then there would be no big deal about that, right? Maybe 10 years ago, 10 years later, that would be the case. And those events are relatively rare, and yet they are strong enough for us to make us worry about the first order effects of importance. Do we have to buy insurance? Are the buildings constructed to withstand the forces of hurricanes and tornadoes of the so-called Category 5 or F5, and what about explosions? Very often, both those events, not always, are localized at least in space and are relatively short-lived in time. They don't go on for a long time. And tornadoes, of course, are small compared to the typical length scales in the atmosphere. And in turbulence, we talk about the small scale. We talk in the middle, so they are on and off. And sometimes there's a lot of activity, and sometimes maybe everything is quiet. And the fluid element, the imaginary piece of the fluid can experience extreme local deformation. You can stretch it out, you can make it rotate around, and different things happen. If you think about combustion, if you think about a flame surface where you have the right combination of the concentrations and temperature to have something burning. What about if you stretch out the surface very strongly to the extent that the surface will break? And then in that case, the combustion will stop for a little while. And what about cloud droplets, clustering? Do we have rain? Why is rain so difficult to predict versus temperature? All of that has to do with the small scale turbulence. If we'd like to reach a high Reynolds number, but not only that, we need to resolve the small scale and what to do reasonably well sampling. And on blue waters, we have accomplished the first 8192 cube simulation of the flow homogeneous inotropic turbulence. Actually, is similar to what we had about the first in the first top. Inotropic turbulence, what is that? You imagine you have turbulence in the air inside this room where there's some irregular motion, and never mind the physical boundaries. And then we'll find out that the statistics are essentially a function of position and going in every direction in about the same way. We want to focus on the fundamentals here. And again, the last talk already we heard about direct numerical simulation. We solved the Navier-Stokes equations, conservation of mass, and conservation of momentum. And like the previous talk here, fortunately we are able to use Fourier pseudospectral methods. They're highly accurate on a per grid point basis. On the other hand, that's a challenge that they are typically very computationally intensive. We have to take transposes in order to do FFT in this direction, x direction. You have to collect all the data along this line. What about FFT in other direction? Now you have to redivide the data somehow. And the what is the most effective methods use MPI, correlate Fortran, which is essentially remote memory addressing, and we have a favorable topology. This morning we heard Bill Kramer talk about the advantages of topologically aware scheduling. We have benefited greatly on that. We were using 256K cores, and we get just under 9 seconds per time step. And what about if we use one quarter, use 64K, and we get 30 seconds. 30 seconds divided by 4 is 7.5. 7.5 divided by 9 or so. You see that we are getting pretty good scalability when we talk about essentially a factor of 4. And what if we did not have a favorable topology? Actually, we would be operating at least twice as slow. So it was a very quick improvement. The I/O will be found to be very fast. We're able to write about 4 terabytes in a minute or less. We have some post-processing capability, and we also try to do some processing while we're on the 5. And we are using the visit package for visualization. One of the problems here is that although on one hand we try to make the code as fast as possible, on the other hand we have to worry about how many time steps do we need. That depends on the physics. And last time we heard about Sij, the strain rate. Another way of thinking about it is the symmetric part of the velocity gradient tensor. You have a different velocity components, and it can vary in different directions. That's why we have a 3x3 tensor. And a high dissipation rate would cause a rapid shape distortion of the surfaces. If you think about going to a birthday party, if you blow at the flame, that candle very hot, what you're doing, you are stretching out the surface. At the same time, the pollutants, namely that little bit of smoke that we tolerate from the birthday candle, that will be spread around the room. On the other hand, what about if you just let everything rotate around? Then that's a different thing. What about tornadoes? That kind of swirling motion tornado. Well, if we have a tornado, we don't get something move 10 miles away from it. It's still relatively local. And the basic question for us is how intense are those extreme fluctuations? How likely they are? How do they behave? How do they form? How long do they live? And what is the size? And how do they affect the important processes of turbulent mixing and dispersion? And we'll get to that later. So we require high Reynolds number at small scales where we solve. So what about the likelihood? We talk about probability. Probability here, but the quantity to look at the probability density function. Much like the probability of something falling into this unifold divided by the size of the unifold. So we're talking about extreme fluctuations. Extreme fluctuation on a scale here, I may not be very clear, I'm sorry. So the left-hand side here, 0 to 300 times the mean. And down the middle, 0 to 2,000 times the mean. On the right-hand side, 0 to 8,000 times the mean. And you see that the probability goes down. Certainly, the question is, one of the questions we ask in turbulence research is whether dissipation and so-called entropy, which is essentially about the rotation rate, which one is more intermittent, which one has the tails going, what we call the tails going further out, and why should we care? Well, and why are we surprised if they are different? Because they're both measures of the small scales, and they have very different physical effects. If we are looking at relatively low Reynolds number, Petascale Reynolds number 240 here, we will say that, I think everybody will say that these two curves are different, solid lines and the dashed line. If we have this graph in the middle, which should appear in the paper 3 years ago, if we are going to look at this here also, we'll say that they are different. But yet, if we take the sampling way out here, we find that these two curves start to coincide upon each other. And the tendency is even stronger at 8192 cube with a high Reynolds number. And also, we see that you have to go to 5,000 times the mean before you see that these two curves are really coming together. And there, at 4096 cube, maybe it will be something over 2,000. So that's one of the things that we couldn't be sure of from 4096 cube, and which also, if we did not have sufficient resolution, we might not be able to see it. And what about the spatial structure? In the study of in the turbulence literature, we talk about what we call a local average. You suppose you have something inside a volume, and you integrate it over the volume divided by the size of the volume. You get a so-called a local average, and we could say that that volume has a linear size R, and you can let R go from 0 to L, to go something very small to something very large. And our interest is whether, especially in the middle of some, for R in some intermediate range, is there some particular way to go for us to get a handle on how do things behave. And that has to do with intermittency correction from any classical results in the turbulence. If you have heard about K to the minus 5/3 spectrum, for example, that is not exact. And instead, K to the minus what? We have to know about the divisions of the intermittency. And because of homogeneity, we can take samples everywhere. And so let me look at this here. The PDF. We run our DNS code using a two-dimensional decomposition. There's a couple of tricks for us to recover three-dimensional local averages. And we're mainly interested in averages over subcubes of size relatively small, unique direction, 1, 2, 4, these by powers of 2 up to 64. And then all of these lines here, the lower set of curves are all for dissipation rate. The higher set of curves was for the entropy. They are not actually that different, but I'm artificially bumping up the lines in blue by a factor of 10 to the 4th so that we can see them on the same graph. And the arrows are going in the direction of increasing R. So if you average over a larger domain, then everything becomes less variable. So the PDFs would start would go like this. For example, instead of a small R, you would go be both. You can have both samples that are extremely small and samples that are extremely high. Then there's at least some 10 decades in that. We see that if we look at this very closely here, some of these lines coincide here, but some of these lines do not reach there. But those lines which coincide are those for the smallest R, and this indication that the extreme events are actually localized in space. But about visualization, we started thinking about, can we visualize 8192 cube? But if you think about how many grid points there are, and if someone could make that image, can a human being really make sense of the image? And we think the answer is probably no. So instead, given our emphasis of extreme events, our extreme events are relatively localized. So that means that we don't need the whole 8192 cube. We look at a piece of it. We look at the important piece of it, just like if you look at Google Map and then you want to zoom into that place where you want to go. And that's what we want to do, and we're going to change the contour levels if we do it. And we have some statement to make about whether the geometry of regions of high dissipation as well as high vorticity. We would like to know, whether, for example, whether extreme events are different from those which are less intense. So here we start with this. We have isolated a 7668 cube piece subdomain of the entire 8192 cube. And the color in red represents a high dissipation, and the color in blue represents a high entropy. So this is contour level 10. Thank you. So this is contour level 10. You see a massive detail. And now let us increase the contour level. You see that the the volume occupied by the contour surface becomes smaller and smaller. Of course, that's what we expect. At some point now, we start to make the image larger, and then we move the image up to see this particular structure, which I think is interesting. And if you raise the contour level even higher, and eventually it will break up. And this is the 31 cube subdomain. Okay, so that is the kind of image that we have gotten. And then we, of course, one might worry, well, there's only one instantaneous snapshot. What is this representative? Here the images from 3 snapshots. At 1, 2, and 3, they're all from 8192 cube. You see that they have the same kind of thing. They're not, you have red and blue almost coinciding, and there's some other isolated short, long filaments in blue. On the lower right-hand side, this is at a lower Reynolds number. You see that it's quite different. You have what we call a vortex tip, and it's wrapped around by the red surface of high dissipation rate. And we also wanted to say something about evolution in time. But I realize that I'm running way out of time. What I would say, let me look at this here. Imagine that if you are talking about observing some kind of tropical cyclone, it starts at a tropical depression, I'm sorry. And then it becomes a tropical storm, and then becomes a hurricane, and then we may become a Category 5 hurricane or typhoon. And then it won't stay there for very long. So you go from Category 3, 4, 5, and then it comes down to 4. So these are the kind of things that we are seeing, that we get peak values 10 to the power 5 of the mean almost, but they're not very long lasting. Yeah, we can get some idea about how long they last. And then this is another image where we're not zooming in. We're looking at the fixed subdomain, and we will see as a function of time, as a function of real time, how things change, and you'll see that the structures grow, and then they move to another place, and then at some point they would disintegrate. They would start to disappear. And what is new? And I think there may not enough time for me to go through all of this. But we should also ask ourselves: is the question, are results robust? Is it affected by resolution, sampling, and as well as precision? And we have a manuscript we're working on that we want to submit to the proceedings of the National Academy of Science. And the implications of this, I think we have more understanding of turbulence, and also that we're going to use that for improving theories of fine scale intermittency. And I think our experience of facing the challenges in petascale computing has been worthwhile. Well, why blue waters? I think hopefully that is already clear. And we're going to study Lagrangian intermittency, as you say. Instead of observing what happens at a location, we will try to follow the path of the fluid. So we will have an observer following the fluid, and that's very important in the study of pollutant dispersion. But we have to improve our code a little bit in order to make our next series of production ones. And also for turbulent mixing, one simple way about demonstrating turbulence is just if you have a teacup or a coffee cup, you stir it. Well, what happens? The concentration becomes uniform very quickly. That's the result of turbulence. So that's what I like about turbulence myself, because you don't have to go to a lab in order to experience it. We have it every day. And the concluding remarks here, I think with our large allocation, hopefully we have, hopefully other people will agree that we have done something useful, and we would like to keep working on it. And our next target is to try to study turbulent mixing and dispersion. And for long-term goals, if we have blue waters too, I think we won't be short of some topics that we want to investigate. Thank you very much. I'm sorry for running out of time, but
we have time for 1 or 2 questions, and I'll remind the speaker to repeat the question, and just for recording's sake.
Yes.
What is your I/O model for getting 4 terabytes per second?
I'm sorry.
What is your I/O model for?
What is the I/O model?
Yeah, you're just writing it
We are doing the primitive thing, 1 file per process. Well, wait a minute, take it back a bit. We are doing two things. Before December of last year, I was writing 1 file per process, and now I'm writing 1 file per communicator. So basically, instead of 256K files, I have about 8192 files. But IO seems to be very fast. Yes, thank you.
Other question?
Yes.
Do you run this code in any other Petascale system?
We have run the code on SAMPit. We have run the code on Titan. I think performance between SAMPit and Blue Waters, Titan and Blue Waters is similar, but then I think we don't have that advantage of being able to pick up a favorable topology. So on Titan, we're limited by the by communication. On SAMPit, another question is SAMPit seems to be open to everybody, so we can get a big job done. Yeah.
So you mentioned right at the beginning of your talk that you use co-array Fortran.
Yeah.
Have you found that to be useful for code development?
For
code. Has the use of co-array Fortran as opposed to just plain old Fortran plus MPI helped performance or scalability? Writability in some way?
Yes, it helped. But, well, it was Bob Frieder of Cray who helped with us with co-array Fortran, and we're using it to for transposing the data. It definitely helps, although now with topologically aware scheduling, in fact, it seems to matter less in an ironic way. But because our codes have been dominated by communication, anything that makes the communication faster would work for us.
Okay, let's thank our speaker.
Thank you.